So the review starts on this page, right? Make sure that you see that okay? Let me turn the fine up. All right. So if we look, we have all these questions. Key thing: frequency is F. This lambda sign is wavelength. Speed of light is c, and the Planck's constant is h. All of these formulas will be given to you. Does anybody remember the point of distance between one wave to the next wave? Is it frequency, wavelength, speed of light, or Planck's constant, or amplitude? Anybody? The distance of one wave to the next wave. Amplitude, speed of light, wavelength, Planck's constant, or frequency?
Wavelength.
Wavelength is correct. It is the wavelength. What's the symbol for that? Well, that is the lambda. What do we call the number of waves that travel per second? That is the frequency, wavelength, speed of light, or Planck's constant. That is the frequency. Anybody know the unit for frequency? X103, 103.3 watts per second. If you ever dealt with radios and amplifiers, you might have seen this, but frequency, the measurement is
hertz.
Hertz. Very good. Who was that?
Seth.
Seth. Okay, you made it. Okay, cool. That's what I thought whenever you said it. I was like, wait, that's Seth. I had you marked down as absent. I'm going to change that real quick. Hertz is correct. Good job. These true false. Electromagnetic radiation can travel through the vacuum of outer space. That is true. Remember, the electromagnetic radiation is radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. All of those can travel through the vacuum of space. How fast do they travel in the vacuum of space? They travel at the speed of light. Ultraviolet, is that one of the ones I said? Yes. Is sound in there? Can sound travel through space?
No.
Nope. So sound is not an electromagnetic radiation. Mechanical energy? No. Radio waves? Yes. If white light is passed through a prism, we see the rainbow. We saw that with the different colors and that little piece of those glasses that some of the students had in here. A quantum of electromagnetic radiation is called a photon. All forms have the same frequency. This is not true. They all have different frequencies. The wavelength of a photon is directly proportional to its energy. Well, let's see. What is the formula? Energy equals hc over wavelength. As this goes up, what happens to this? This goes down. So as one goes up, the other goes down. This must be indirectly proportional then. A photon that has 3 meters in length has less energy than one with 1 meter. The more or the higher the frequency, the greater the energy. So yes, this is true. 3 meters has less energy. You can think about it too. What if we take this divided by 3? It will be smaller versus this divided by 1. According to the Bohr equation, Bohr electrons orbit the nucleus like planets. This is true. They don't use gravity though. They use electrostatic forces. So So the positive and negative, the positive charge of the nucleus and the negative charge of the electrons attract each other. Electrons are, there we go. Yeah, this is false. It should be electrostatic forces. This is how much energy of a photon with a wavelength this. Well, we have the formula up here. We're going to rearrange that. So wavelength equals hc over energy. Hc, both of those are constants. H is 6.626 times 10 to the negative 34th. We're going to multiply that by the speed of light, which is 3 times 10 to the 8th meters per second. We're then going to divide that by the energy, which they gave us. Oh wait, I'm actually, I don't need to switch that. I actually can use this formula. I thought for some reason they were asking the wavelength. Oh, I probably read this one. Let's do this one first, since I already have all of that into the equation. What is the wavelength of a photon with the energy of this? So I'm going to divide this by the energy. 7.22. We get the energy of 2.75 times 10 to the third. Or the wavelength is 2,753 meters. All right. So this one, we're going to use this formula up here. How much energy of the photon of a wavelength of 156 meters. So I can actually keep this 6.626 times 10 to the 34th times the speed of light. This time I'm going to divide that, instead of by this, I'm going to divide it by 156. Boom. And we get 1.27 times 10 to the negative 27. Easy enough. Use the Bohr equation to calculate this. So what you do with the Bohr's equation, if you recall, it has a set number. That number is negative 2.18 times 10 to the negative 18th. We're going to take that 2.18 times 10 to the negative 18th. And I believe it's negative, right? Just had it. Yep, negative. And you're going to divide that by n squared. N is the level, so the energy level. So it's the 7th here. So I'm going to take negative 2.18 times 10 to the negative 18th. And because that is the 7th energy level, I'm going to take that divided by 7 squared. And so we get, for the 7th one, negative 4.45 times 10 to the negative 20th. If I want to do the 8th one, all I got to do is go up there and change that instead of the 7th to the 8th. And we get negative 3.41 times 10 to the negative 20. If we take a look at these, which one is closer to 0? Well, since they're negative numbers, it would be the negative 3.41. So this has the greater amount of energy, which makes sense because, as we said, the further you go away from the nucleus, the more energy you have. And if you're the 8th energy level, then you are furthest away from the nucleus versus the 7th. It says if a hydrogen electron moves from 1st to 2nd level, what will be the energy? Will the energy be absorbed or emitted? If it goes from 1st to 2nd, that's going to a higher energy level. It has to absorb energy. If this were going from the 2nd to the 1st, it would be emitting a photon of that energy. Now, how much is the energy? Well, we have to take these two and subtract them from each other, and that will give us the amount of energy. Negative 5.45 times 10 to the negative 19th minus negative 2.18 times 10 to the negative 18th. We get 1.635, so 1.64 times 10 to the negative 18th. So easy enough. That's the first page. Nothing real difficult there. Second page. Remember, an orbital is just a space for electrons to be. Each orbital Like for example, the 6f orbital and the 12s orbital, each orbital can only hold 2 electrons at most. Doesn't matter how far away from the nucleus it is. For example, 6f is pretty far away from the nucleus. Doesn't matter what sublevel it's in either. A 5p sublevel is just like a, oh, there's no other one. A 5p sublevel is just like a 4p sublevel, except it's a little further from the nucleus. They all the p sublevels hold 6. That's because they have 3 orbitals, right? An F orbital, I'm sorry, an F sublevel has holds 14 but has 7 orbitals. D holds 10 but has 5 orbitals, and an S only has a 1 orbital. P's have 3. If we were drawing this is the P4. We have a 3p4. There are 4 electrons in here. When we put electrons in, remember each one gets 1 before any get 2. So we put the first 3 up, and then the 4th one goes down. Which sublevel represents the most potential energy? It's going to be the furthest one down. So in my mind, 5D is winning. If we take a look, here is 6S. After we go from 6S, we go down to 4F at 57. We go all the way across 4F, and we come back up to 5D. Remember that the Ds are always one behind the major sublevel. So 5D is going to be the one that is picked there, 5D. Remember, if we have a positive charge, we've lost electrons. If we have a negative charge, we gain electrons. So we define erbium. Erbium has normally 68 electrons right here. So 68 minus 3 is 65. When it comes to periodicity, which 5th period element? The 5th period has the smallest atomic radius. So we find the 5th period. We have rubidium, which would be the largest. And we have xenon, which would be the smallest. Because as we go across, the nuclear charge pulls the electrons in closer, which 2A element would be the largest. So here is 2A. We start with 2S sublevel, so the 2nd principal energy level. As you go down, we get all the way to the 7th principal energy level, which is going to be further away from the nucleus. So that is radium. Yeah, radium. So Ra, radium. Basically, you keep doing that. Keep in mind the ionization energy is the energy to remove an electron. As you get smaller, that energy becomes bigger. So if you are large, the electrons on the outside are going to be easy to take. And the electrons that are pulled in tightly are going to be more difficult to take. And look at the last page. Here, let's do one of these. Let's do the full of copper, and then we'll abbreviate it. I'm sorry, chlorine. So we want chlorine. So we need to start up the top. 1s2, 2s2, 2p6, 3s2, 3p5. So 1s2, 2s2, 2p6, 3s2, 3p5. And we want to abbreviate this. So we're going to go find 2p6, figure out which noble gas it is that is neon. So we will put neon there. And then that will take care of all of this. And then we can go 3s2, 3p5. That is the abbreviated form of chlorine. Any questions as I've gone through that? Anything you need to see again? So I'm going to allow you guys to remember that I said this yesterday, I believe, you know, if you watch me do chemistry, that is not as good as you trying to do chemistry on your own. Like watching Michael Jordan play basketball and then go out there and be like, I'm going to hit all these 3-pointers now. Not going to happen. You need to practice of your own. I'm going to give you the time to do that. If you do have questions, the Zoom will be open. But I'm done. You're more than welcome to stay if you do have questions. Oh, there's somebody putting in the chat. Remember, I never look at the chat. I'm here. Oh, thank you. Miss Jackson, can I slow down? Well, it's a little bit late for that. Omar, sorry. Page 20, questions 1 and 10 and 11. Which page is page 20 move?
The last page.
The last page, number 1. Let me get Emily. Sorry about that, Emily. I got you. Is there anybody else that came in late? I got Kashan as well. Because he answered a question, and Seth because they answered questions. If you didn't answer a question, I don't know you're here. So keep that in mind. All right. So I'm still sharing, right? Oh, you can't see it though. Questions 1. How many electrons are in the second energy level of each of these? So one way you could do that is you could do this 1s2, 2s2, 2p6, and then you add up anything for the second energy level. So basically 2 plus 6 is 8. For fluorine, it's going to be different. For fluorine, it'd be 1s2, 2s2, 2p5. So 5 plus 2 is 7. And then questions 10 and 11. How many electrons would be in the highest occupied energy level of a barium atom? So we find barium all the way down here on the periodic table, all the way down, right down here. And that is 6s. So how many electrons are there? 6s2. That would be 2 electrons in the highest occupied energy level, which is 6. 11, how many electrons would be in the highest energy level of a lead atom? So this one's a little bit trickier because we have 6s and 6p. I'm going to ignore the 5 and the 4 because they are lower than 6. So we have 6s2, 6p2. So that's 2 plus 2. That's going to be a total of 4. Anything else? All right, guys, get out of here. Have a good weekend. The test is Monday. It's asynchronous, so you will just log in to take the test any time of the day. Doesn't matter to me, but you only have 60 minutes to complete the questions. Please study today and email me today because I'm not going to be available over this weekend. I won't have computer access. So please keep that in mind. Have a great weekend. Bye.
How many questions are on the test?
So it's usually going to be like 33 questions because each question is worth 3 points.
Okay, thank you.
Yep.
Thank you.
You're welcome. Have a good weekend.
Thanks.
You have a good weekend too.
Hey, thank you very much.
Have a good weekend.
Hey, take care. Tori, you good? I'm gonna go ahead and end it so I can put this recording on, but I'll open it right back up.